So in this lecture for Industrial Studies 3050 Intro to Metals, we're going to discuss metal casting. So generally, metal casting processes are broken up into three general categories: sand or aggregate molds, metal molds, and specialty molds. So we're going to start out with sand molds. Typically, sand molds are green sand, or it's the most popular anyway. And when we say green sand, what we mean is that it has moisture in it. It's not green in color, usually, but it's usually more of a black color. It represents kind of like when you have clay and it's not dried out or fired yet. It's called greenware or green. And it means it has a little bit of moisture in it. So we have silica sand, we have bentonite clay, and we have water. Now, bentonite clay is used in a lot of applications, one of them being drilling operations where they put bentonite clay down around the drill to support it, and also to help bring up the particles of rock that are ground up when you're doing drilling for, let's say, oil. Anyway, so 6 to 8% of this bentonite clay and 2 to 3% water. Typically, the ratio between clay to water is 1 to 3, or 3 to 1 if you do clay to water. Okay, if you put too much in, the sand will be kind of wet and stick to the surface of the pattern. If you put too little in, you won't have enough strength. So the resulting castings might have a bad surface finish if you put too much water in, and if it's if there's not enough, it will fall apart. So generally, a pattern is usually a positive shape when we're doing sand castings, especially green sand castings, and you need a positive shape slightly larger than the final part. And what happens is, as metal cools, it will tend to shrink. And what I mean by that is the bar starts out, or something I'm casting starts out at 12 inches. After you cast it, it's going to be some distance smaller. And the reason for that is, as it cools from a high temperature liquid to a low temperature liquid, it shrinks a little bit. But it's still the same volume. It occupies the same mold, right? So you pour it into a mold and it starts to shrink. And then we put a riser on that to help feed that shrinkage. Okay, so you may have seen that in the videos. So as it goes from liquid to solid, it also shrinks. But once it becomes solid, it is the same shape as that mold. Okay. As it cools down from a high temperature solid to room temperature, as you know, when you heat things up, they expand. When it cools down, they contract. So you're always going to have some contraction from a casting. And the cool thing is, nowadays we can do something easily about that. What we can do is we can take, and in SolidWorks or some CAD program, we can say, scale that part of the pattern I'm talking about. You're going to machine it, or you're going to somehow 3D print the pattern. And so you would print it at like 1.02 scale factor, which means 2% would be a typical, 1 to 3% would be a typical shrinkage that you would get as it goes from high temperature casting down to low temperature. So we just scale the pattern up, and then we're good to go. Our final part then will have the right size, which our customer is going to demand. Okay, the pattern itself needs to have draft on it. And what draft is essentially, if I put something square, like a block, into the sand, and I just try to pull it straight out, and what's going to happen is, the sand is pretty good in compression when it's all the sand grains are all compressed together. But if you start pulling on sand grains, they'll fracture very easily. So in tension, the green sand is not very good. In compression, it's fine. It has a relatively good strength. So what we're going to need is a little bit of angle on the sides, kind of like ice cube trays. Okay, so if you ever made ice, getting it out of the tray sometimes is difficult, but it has a taper going up. That's called positive draft. If my pattern doesn't have positive draft on it, then my part's not going to come out of the mold. Okay. So the draft angle, you might have somewhere between, a half degree. Some have no draft on them, but most of them have a positive draft. When I say some have no drafts, some of the castings that we make have no draft. And depending on where that surface is, you really only need draft on the sides of the part, because the top of the part, the sand comes straight off. But the sides of the part, as I pull the sand off, they're going to need to have draft on them. The parting line divides the cope and the drag part of the mold. Okay, so usually the ones you've messed with, well, I guess you guys have done, you did your irregular parting line. So some of them, they don't have to be a plane. It could go up and down around the airplane or around Bert and Ernie or whatever you're casting. And so the parting lines don't have to be flat. In fact, in industry, most parting lines are very irregular. And it takes a lot of thought to figure out how to run the parting line in order to get that part out so that you can make thousands and, they come out of the mold really simply. Okay, and then a match plate is just where we fix a pattern to both sides of the plate and we ram sand on both sides. It'll have all the gating and everything in it, and it makes it easy for production. Okay, these terms are all in your book, and you should be reading along as we go here. A core is a piece of sand that's bonded together with resin or some other binder, and it makes a hole in the casting. It's held on the end by something called core prints. And the core is produced by a box in which sand is forced and held until it cures. In other words, we use a different kind of sand for that type of operation. Okay, so a core print is in the ends of on the ends of the part, and so like let's say kind of corn on the cob, you got to hold it from both ends. So a core, if you're going to make like say a tube, you're going to have a core running through the center of it, right? That core is made out of hard sand that can withstand tensile loads. Okay, so when you cast the molten metal around that core, it makes it hollow, sort of, but it's got a bunch of sand in it now. Well, how do we get the sand out? You have to chip it out, or if that sand was bonded together with some sort of a resin, like a plastic, the plastic will degrade and fall apart so that the sand can just flow out. Think about an engine block where there's lots of water passageways and stuff like that. That's how they're made. They're made with the core to form out those internal passageways. Okay? Okay, so things you're going to need to play in the sand. Okay, so this is like we're talking about going in the foundry. The things that you had a riddle that was that sieve that broke up the stuff and kept things away from your pattern. I remember at the foundry that I worked at, we had straw brooms, and every once in a while a piece of straw would poke out of the mold, and you'd have to carefully pick it out. So if you filter it with the riddle, then that helps keep those things out. Cigarette butts, things like that. A rammer is that little thing that packs that little wooden part that you guys were using. Sometimes they're aluminum. It packs the sand together. A sprue cutter were those metal tapered things that we use to cut the sprue. Now, and typically we would cut it after we make the part. That sprue is tapered, and the reason why it's tapered is because as metal falls, it accelerates due to gravity, right? So, as we know, like a fluid occupies some sort of volume. So as it falls, it's going to have to constrict in cross-section because it's accelerating. It's going faster. Okay, so as it falls, it actually gets thinner. It's like almost like you're stretching it out. Okay, and so in order to not have turbulence on the side, what you need to do is taper that sprue slightly so that so the flow is always touching the sides. Otherwise, you have erosion, kind of like erosion on a shoreline, or when rain goes across, rainwater goes across a mud surface. Okay, some other terms. We have the flask, which is what we compact the sand into. The top of it's the cope. The bottom of it's the drags. The drag typically has the pins, at least in the United States. A slick and spoon are those tools that you were using for cutting and the gating. And if something breaks, you can kind of put it back together with the slick. Usually the spoon is to carve sand. Parting compound is that white powder. It's kind of like a talcum powder that keeps the sand mold from sticking to itself. Okay, so what is the gating system made out of? Okay, so it's essentially a network of channels that help fill the mold with molten metal. It's really important that these channels are done properly, and that's the big secret to making castings, is to have the proper gating system in order to ensure the highest quality part. Now, depending on your customers really are picky about what their parts look like. So if you have say a haphazard gating system where the metal flows in and it causes erosion in the mold, what can happen is you actually get sand particles in your casting. And you may have seen that on your casting. You may have commented on that as to one of the defects. So you want to avoid that. And the way you avoid that is to do some calculations for gating. And so that's one of the things that you'll learn if you take any of the casting classes. We'll talk about how to get the metal to flow in the casting from the pouring basin through the sprue base, if there is one, the runner, the gate, and then the casting. Okay. Sometimes in here there's something called a riser. And a riser is, we talked about it briefly, it is a reservoir of metal that stays liquid longer than the casting. And that's key, actually. I'm going to say that again. A reservoir of molten metal that stays liquid longer than the casting. So if you have a really compact round shape, you almost need a shape bigger than that to feed it. So your yield, how much casting you get for how many pounds of metal you poured, is going to be pretty low. Okay. If you have a thin, spindly casting, they tend to not shrink so much, and or the shrink is distributed over the surface and you can't see it. So we can make those a lot of times without any risers. Okay. So the yield is probably pretty high. So it kind of depends on what kind of castings you're making, what you're going to get. So let's look at why we would use a riser. Well, again, the liquid metal above the melting temperature, so that's called superheat. It goes in above the melting temperature and it shrinks as it cools. Okay, we need to use a riser. So that liquid metal, as it goes from a high temperature liquid metal to where the temperature it's going to solidify, it will need a riser to feed that shrinkage. Okay, as it goes from liquid to solid, sometimes like aluminum might shrink 6%. As it goes from liquid to solid, then that needs a riser also. Again, that's a reservoir off to the side. And then we have another shrink when the metal goes from a high temperature solid to a low temperature solid. And this is what we talked about before. But what I didn't talk about is that that's called a shrinkage allowance, that factor that you apply in SolidWorks in order to scale up your part so that your actual part, your pattern, so that your actual part comes out more or less the shape you want it to. Okay. So looking in your book, it's kind of an older book, so some of the terminology is a little bit goofy. Lost foam casting, otherwise known as evaporative pattern casting, and in the book it calls it full mold casting. So that book was written a long time ago. The funny thing is with lost foam is this type of this process of sand casting is already come and gone to some extent. It was invented probably somewhere around the 70s. I think it was by an artist actually, where you're actually going to take and pour molten metal into right on top of some styrofoam that's just embedded in the sand. And what happens is the styrofoam will vaporize and or melt, and then as the metal flows behind that melting styrofoam, it puts pressure on the walls so the sand can't fall in. And amazingly, you can make really accurate, cool castings. In fact, if you are looking to make anything in your garage, you would probably want to try the lost foam process, because lost foam is all you would need is a garbage can with sand, a metal garbage can, and then a foam pattern that you make by cutting with a hot wire, gluing some things together. There's a couple tricks to it. You put a very, very thin coating of a ceramic on. You don't have to, but you get a much better surface finish. You put it down in the sand, and then you shake sand all around it, and then kind of vibrate it, compact it so the sand gets in all the little nooks and crannies. And then you pour molten metal right on top of that little piece of styrofoam sticking up, a sprue sticking up. You have to have a gating system. And then it vaporizes and you have a casting. So check it out online a little bit. But lost foam casting is a pretty cool process. It was used, first product they made with it was the Ford Taurus. This is high production anyway. The Ford Taurus used it in the intake manifold. I think it was a 6-cylinder. And then I think General Motors pretty much took over. They made the whole Saturn engine was based around lost foam casting. So General Motors embraced it for, about 15 years. And then to some extent, they've discarded it now. They don't even I don't think there's any lost foam castings available or still in production for General Motors anymore. They're making their sand a different way. They're making their molds a different way. So the way they're making them now, it says dry sand. This is something that talks about in your book. It's not really used anymore. Dry sand could be oil bonded. It could be, you use a sodium silicate binder. It's mixed with sand, and then you put CO2 through it, and it cures it. It's kind of magic, actually. We do this in our lab. So you mix sodium silicate with sand. It makes kind of a wet sand, feels just like sand on the beach. And then you pack it into a mold, and you blow CO2 through that sand with like a little suction cup or blower kind of thing, and it blows this. You actually blow CO2 through the sand, and now you have a cured, really hard mold. Okay, and because you had to bond these things with like CO2 or something like that, they came up with something called AirSet, which doesn't need any external catalyst like carbon dioxide. It can use you can use resins that have a chemical catalyst. And so what you do is you mix them together, and you get a certain amount of time to work with them, just like epoxy or fiberglass, and then they cure and form a mold that's very hard, almost like a rock. And those we can use for either cores that go in a casting, or we can make the whole mold out of it. Okay. You're going to have to look in your book on this one and look around a little bit. Shell molding is a process whereby it's actually invented by the Germans, I believe, in World War II. Cool thing about winning the war is we got all the patents that happened during World War II, so we kind of stole it from the Germans. But what you do is you take and make a pattern that is hot, like 400 degrees, 500 degrees Fahrenheit. And then you take some sand that has a resin coating that cures with heat, and you just drop it on top of this pattern. It cures for a while, and it cures a thin layer of material. Then you pop it off, and the unbonded sand falls back into the system and can be used later. And now I have this, let's say, half of a mold of of sand bonded together with resin. Okay. Then what do? Well, I take 2 halves of that, put it together, and pour down the edge, or you can break a piece of the top off and pour into it. So shell molding gives you really smooth castings. So smooth and it doesn't use very much sand when you make a mold. So let's see what it says here. Thermoset resin is cured against a heated mold, 400 to 600 Fahrenheit. Can be used to make hollow cores or complete, entire molds. Thin wall decreases sand use. The sand can't be reused, though. That is a disadvantage. Okay, next one we're going to talk about here is permanent mold castings. And by the way, I'm going to put some, as we go through these processes, I'm going to put some videos that you can watch that back some of this up. I know I don't have a lot of good pictures in this PowerPoint. It's pretty dry. So what you want to do is maybe look in the attached videos and watch some of these videos on these different processes to get a better understanding of what I'm talking about. So please do that before you go on to taking a quiz of any sort. Okay, so permanent mold or gravity die casting, essentially usually a cast iron mold, but it can be other materials, steel or something. And you pour like aluminum or some other lower temperature melting alloy into it, brass, and you can use that die over and over again. The thing you do have to watch out for is it does get really hot, so it needs to be cooled either by water or by air, usually by air. And you can make a lot of castings, but remember that the cycle time on this is completely dependent on how fast you can suck the heat out of the casting. Okay, die casting, you know what these are. Hot chamber zinc die casting. What is that? Well, Matchbox cars are made this way. So a small little, all those die cast little models and stuff like that, they're all made with high pressure die casting, usually hot chamber, which means there's a video on it. You want to watch you want to know the difference between hot and cold chamber. I'll tell you briefly, but you want to back that up. So hot chamber means that the molten metal surrounds the piston that actually shoves the molten metal into the cavity. Okay. Cold chamber is, and this is where it's confusing, hot chamber is used for lower melting temperature alloys, typically, like zinc. Cold chamber is used for hotter alloys, like aluminum, because we want to minimize the time that the molten metal is in contact with the shot. There's like a piston that pushes it into the mold. Okay, so essentially we're pushing molten metal into the mold at really high pressures, like 10,000 psi or something like that. So the mold fills up very quickly with molten metal, and you can make really, really thin little castings. Okay, little or big. There's probably some parts in your cell phone that are zinc die castings, little itty bitty fittings that they have to do something with, I don't know, like a lead or something in there that supports something. They're probably in your phone. Okay, and they're miniature. I mean, you can hardly see them. Little bitty things. Okay, so high pressure die casting. It's kind of a different animal. The dies are made out of really high temperature steel. They're very very expensive. So a die might be millions of dollars, truthfully. Mercury Marine is probably the most advanced cold chamber die casting. Well, actually, they do hot and cold chamber, but die casting company in the world. They're making right now a V8 engine block as a die casting, and who knows? You might see something new on the horizon where they have even more horsepower. Okay. Okay, some other processes that I'm going to explain these briefly, but I'll put some videos up on these and investment casting, where we take a wax part. So essentially, usually they have a aluminum mold. They inject a wax part into it. That wax part cools, pops it out. So it looks just like a plastic mold, right? So you just molded this plastic thing. Wax is not very much different than plastic. So now we have this wax that's the shape of the part that I want, but it's a little bit bigger because remember that pattern, that shrinkage stuff? Okay, the metal shrinks. Then we dip it. We attach it to a sprue and we dip it in a ceramic. And that liquid ceramic coats the outside of it. And we do this like 10 times so we get this nice thick layer of ceramic on the outside. You melt out the wax, you pour in molten metal, and now you got your casting. So that's the long and short of investment casting. So we got the next three have to do with rotation. Centrifugal casting is pretty cool. That's how they make pipe. So centrifugal casting, you would take a round tube, usually. You pour, it could be horizontal or vertical, doesn't matter. And you spin it really fast and you pour molten metal. It sounds like a really dumb idea, but you pour molten metal into this tube that's spinning. Eventually what happens is the metal develops velocity, goes to the outside of that tube, and is now rotating at the same speed as the tube, and it's held out by this centrifugal force, we get tubing, like cast iron pipe, things like that. I'm actually looking at a cast iron pipe in the wall over here that was made on a centrifugal casting machine. Metal Tech in Waukesha does centrifugal castings. They do pipe, lots of it. And they make all different types of alloys. In one of their facilities in Sandusky, they cast pipe. I think it's about 4 foot in diameter. So imagine something that's rotating like 800 RPM, 4 foot in diameter, and they pour molten metal down the inside of it. It's got caps on the end that keep it from coming out. There'll be a video. So, okay. Semi-centrifugal, usually done vertically. Essentially, it's spun this way, like a turntable. You pour molten metal down the center of it. And the deal is there's many G-forces on the outside of this casting. In the center, there's no G-forces, right? Because it's not the actual center is just rotating around. So as we go from the center, we get better mechanical properties because, out here we got all these G-forces and they're really helping to make this metal solidify fast and keep the shrinkage out of it and all that kind of stuff. But in the center, one thing you could make this way is like a fan hub or something like that, where the center of the fan is where the shaft is, and the outsides are where the blades attach. Okay, a friend of mine had a foundry that used to make those parts. And centrifuge casting, this is a little bit difficult to describe, but the whole mold itself is out at the outside edges, and that mold will accept metal. The whole mold is out there. So you might have 10 molds around, and you're pouring in the metal, and there's a bunch of little gates that go out to the outside. This is how they make costume jewelry. And if you're into like any of those war games like Dungeons and Dragons or Battle, I don't know, all those things, Battle Lords or whatever it is, they make the little figurines. Okay, actually, there's a place in Madison that does them. They do all kinds of, and they use a rubber mold. Okay, so they have a rubber mold. They centrifuge it into the outside of it, and they can cast little bitty things that are pretty amazing, actually. Okay, they do stuff for like Disney and the Franklin Mint and all kinds of crazy stuff like that. Okay, so what else? What other processes? Slush casting, this is not done very often. It's usually done for something decorative, where you have a mold that's relatively conductive. You pour a special alloy into it. I think it's a tin aluminum alloy. And then it starts to solidify. You pour it out, so the inside of it's hollow, so you don't have to use as much metal. You don't have all that shrinkage stuff. And then you let it cool all the way down, you pop it open, and now we have this really detailed part. In the olden days, lamps were made this way, like the really ornate lamps and stuff like that were made with slush casting. I think they still use it for a couple things nowadays, but not too much. Mostly decorative. And silicone rubber molding. I did talk a little bit about that with the centrifuge process, but you can just take and make a silicone rubber mold and pour molten metal into it. Now, normally at this time of year, just after Thanksgiving, I have these rubber molds that you can use to cast little ornaments. Unfortunately, you don't get to do that this year because we're not in person, but that's what we usually do at the end of the semester. So those are some of the processes in casting. I know this was a very brief overview, but do read through the section in the book on metal casting, the unit on metal casting, and there's actually several units on metal casting. And then watch some of the videos in this on this page, and take the quiz when you get all that done and when it's posted. So thanks for listening.